Last one, defining the mixing of surface ocean and deep waters through thermohaline circulation, which is kind of a complex mechanism. So these three things are going to be our focus for today, but we're going to start by looking at the top three things in a little bit more detail than what we did before. Here is just a little bit of a review. So the energy, again, for our entire planet comes from the sun, and the heat energy that drives climate and weather, it's indirectly from the sun. So solar radiation flows from the sun to the earth, and then the earth absorbs the solar radiation and releases some of that energy in the form of heat. So the source of heat energy is actually our earth, and the flow of heat energy happens via conduction, which is shown right here. And then the last thing is this really complex with lots of moving arrows, and we expect you to understand and reason out where all of these arrows are going. So we're going to spend a little bit of time here. But convection is what's driving air currents and water currents across our planet. It's a major component of climate and weather on planet Earth. It's just not going to turn on today.
This thing tells me it's recording here.
Is it following me?
It's following you.
It says it's recording right now?
I think.
For people who watch this, it'll be really interesting. You'll have this little thing about this conversation. So maybe the light is just burned out. What do you think? I don't know. This is what we get when we're not doing these things. All right, so here's the convection cycles that exist on planet Earth. And when we were looking at this with our STEM walkthrough, we basically spent time looking at, well, what are the drivers of the convection cycle? How do we move particles from here to there? And how does the movement of particles, both in terms of air particles and water particles in air and below the ocean, how do those contribute to climate and weather? The concentration of heat energy is, of course, at the equator. And we understand the reason why. It's because it's the highest concentration of heat energy anywhere on our planet. And it's due to the direct sunlight and the exposure to sunlight that the equator gets is much greater than anywhere else on Earth. Actually, there's so much energy here that it's driving everything that we're about to describe. The movement of particles from the surface of Earth, these air particles, they go up into the atmosphere. So you're pushing a bunch of particles from one area to another. So if you remember your PV equals nRT formula from in the past in science, when you're pushing more moles of particle into the same amount of space, you increase the amount of pressure. They're in a direct relationship with one another. So when you move air particles from near the surface of Earth, and they move up due to heat energy, and they move into a small amount of space, when you get out here in the atmosphere, you end up with a high pressure area. Well, things move from high to low pressure, so they, at the edge of the troposphere, all of these particles move over. What you end up over here is with a low pressure system. The particles at this point are extremely cold, they're very dense, they're packed together, and the agents of change for the convection cycle, or convection is an energy circulation in general, is gravity and density. So those cold particles are going to be pulled back towards the Earth. The movement of particles, again, we're moving a bunch of moles of actual matter, in this case air particles, but when they get concentrated near the Earth's surface in a small area, we end up with a high pressure zone right here, and then it sweeps across the Earth, and this sweeping from high pressure here to low pressure here is what we traditionally think of as wind. Feel good about this so far? We know that there's a lot of rain right here at the equator because of all the heat energy that's pulling up and dumping water particles all the time, which is what we saw on the stairs with the golf balls. This is why we have so much precipitation at this area. The reason why has to do with the amount of heat energy that's available in this area on our planet. Here's a couple of things that we didn't talk about because we only looked at this in small detail. Well, some terminology that you'll have to know around this unit is the names of the cells. So the Hadley cell refers to this convection cycle that happens near the equator, between 0 degrees and 30 degrees respectively. And you'll notice there's two. There's one on each side of the equator, one in the northern hemisphere and one in the southern hemisphere. Just below that, or above it respectively, as you move out from the equator towards the poles, is the Ferrel cell, found between 30 degrees and 60 degrees. And then the last one, another convection cycle found between 60 and 90 degrees respectively in the northern and southern hemisphere, and this is called the polar cell. Polar cell is easy. It's near the poles. The other two require a little bit of row memorization to keep straight. Here's something that's very important. We didn't talk about this last time you looked at it. But because the heat energy available at the equator is so strong, it's so great, that it's actually the Hadley cell, the heat energy there, that powers all the other convection cycles. So I want you to notice something really key in this animation. If we're looking at the northern hemisphere, we have the heat energy moving up into the atmosphere from the surface of the Earth, up into the atmosphere here, and then from high to low pressure, and then cold falls back towards the Earth. So it's turning in this direction, and there's so much power here that the residual energy from the Hadley cell sweeps and actually drives the Ferrel cell. You'll notice goes in the opposite direction. These turn like gears on one another, and the reason for that turning in opposite directions is because it's the energy from the Hadley cell that's driving the motion in the other convection currents. So the Ferrel cell goes in the opposite direction as the Hadley cell, and by the time you get to the polar cell, the Ferrel cell is turning that in the opposite direction of the Ferrel cell. The Hadley cell and the polar cell is turning the same direction, but the Ferrel cell turns in the opposite direction. But it's because of the Hadley cell and the energy concentration here that's driving all of those other systems. Does this make sense so far? Before I advance forward too far, I just want to take note of, as you go from high pressure to low pressure in each respective cell, so you're going to go from high pressure to low pressure here, but in the northern hemisphere, things are going to turn clockwise. So from here at high pressure to low pressure, they turn clockwise. This is the high pressure area, this is the low pressure area, and you'll notice the arrows also turn clockwise. And in the polar cell, high pressure here, low pressure here, and it turns clockwise. That's because of the Coriolis effect, the turning of the Earth and the centrifugal motion. That's how we explain that. In the southern hemisphere, it's just the opposite. It turns counterclockwise. What's amazing, and will come up a couple times here in the upcoming slides, is you'll notice at the intertropical continental zone, which is right near the equator, you have two of the strongest cells, where most of the energy is being concentrated, and these cells are driving winds, and they're meeting together right at the equator. So we have a lot of wind power driving weather systems right here near the equator. Feel good? All right, a couple more quick things on the convection cycle, and then we're going to move forward a little bit. But these are the big ideas. The convection cycle as an energy source is driven by density and gravity. And like we saw with the gyres, part of the movement that's really important is cold particles plunging from the upper areas of the density and upper areas of the troposphere. And that movement creates the high pressure at the surface of the Earth. That's very important. Heat rising and expanding, and so we understand both of those principles. It's heat energy and cold particles that have higher density and are more likely to act according to gravity. High pressure areas, we talked about this a lot, but I just want to make sure that you have it, so we're mentioning it again to reinforce it. The pressure is created by the movement of particles. So whenever you have a bunch of particles that have been moved into a small amount of space, you have a high amount of pressure. And that's true when it's hot particles moving up into the atmosphere or cold particles falling down. High pressure particles always move from high to low pressure. And then the last, the Coriolis effect, things move towards, as they move from high to low pressure, they turn clockwise in the northern hemisphere and counterclockwise in the southern hemisphere. I really like this graphic. Part of what I don't like about this graphic is it uses a different name. We'll use the Ferrel cell when we're talking about this cell between 30 and 60 degrees in this class. That's the more proper terminology. But what I really like about this graphic is it shows you how the convection cycle of the Hadley cell, it shows where these winds are. This is where the jet stream that Mr. Hobb mentioned last time he lectured, and it shows you how this is the power of the other systems here. So those arrows going counter to one another like gears. All right, so now we're going to do a little student exercise, and I want you to try to write answers as thorough as you would actually try to do for an assessment. So based on what you've just seen about climate and weather, I want you to try to write an answer. Well, where would you expect on Earth? And when I say where, I mean what degrees latitude, and and then explaining why, giving your reasoning for that, for both deserts, rainforests, and grasslands, thinking your way through that. Then, number 2, I want you to explain where the wind would be going at 36 degrees south. So if you're standing at 36 degrees, where is the wind coming from? Those 2 answers. I'm going to give 5 minutes for this, and then we're going to do a quick turn to chair. You'll know that you're done at your time, and the music will be done. Everybody should write an answer for this. Probably about half time, like what I see in terms of brain is thinking. All right, we're right at about 5 minutes here. We're going to just take a couple seconds, turn and share, and then I'll kind of go over, but just kind of explain what your reasoning is, and let's see if we can get around this as an idea. to document some of the main ideas here, but I just want to use this as a graphic to kind of show some things, and then we'll have this as a permanent way for you to see moving forward once we advance past the slide. But we have a lot of heat energy at the equator, so the first question is, well, where would you expect to find certain ecosystems? Well, we know the convection cycle is driving up a lot of water molecules and dumping them wherever heat energy is going up. So where are some obvious places where you're going to find rainforests? Yeah?
You're going to find them on the equator?
On the equator, absolutely. Where else? There's another place. Where else do you have that happening? Yeah?
Would it be the edge between the polar cell and the ferro cell?
The edge between the polar cell and the ferro cell, which is right here. So you'll notice, according to this graphic, we're driving heat energy up and the convection cycle is happening in this direction. So that's exactly right. We have a bunch of rainforests in Canada, actually a much bigger rainforest with a lot more trees in the Canada area than at the equator. We'll learn more about that later in our class, but also right here in Europe. What about deserts really quick? Yeah?
Like midway, like in the middle of the cell, so in the middle of the happy cell and maybe in the middle of the feral cell, like the Gobi.
So the Gobi Desert is one example. We're close there, but not quite perfect.
It's right around 30 degrees.
It's wherever we have the plunging of the particles, and they're going to be really dry because they've lost all their energy. So it's right around this 30-degree area. But you can see there's a band here. So from the edge to the middle, some of the deserts can be quite large. But a lot of deserts found, most of the deserts found around 30 degrees. And where else would deserts be?
Would it be on the same end, but on the southern side as well?
On the southern side as well, like here.
Yeah.
Where else is the edge where cold is falling down?
Oh,
The polar cell, Antarctica, and the North Pole. Those are also Arctic deserts. Hardly ever have precipitation in Antarctica. The grasslands, where would that be? Where do you think grasslands would be? Somewhere between rainforests and deserts, agree? So probably in the middle of these cells. Beautiful. All right, quickly on the next one, at 36 degrees. So this is the equator. Here is 30 degrees. 36 degrees is probably about right here. So if you look and you can see right here by the arrow, things are moving from high pressure to low pressure. So they're moving towards the south, but they're also moving from the west to the east in a counterclockwise fashion because of the Coriolis effect, because we're in the southern hemisphere. Feel good? Those are the answers to those two questions. Here is high pressure. Here is low pressure. High to low. And counterclockwise due to the Coriolis effect. Got it? Beautiful. Here are some of the answers documented. We'll leave this up so that you have it for a reference point. But I'm going to continue on here. Now we're going to take a quick look at how water is moving in the ocean. And the good thing is, if you're buttoned up on the convection cycle and you understand about trade winds and movement of air particles, then what happens in the ocean is going to make a lot of sense as well. So, this is from the textbook, and it shows a bunch of the ocean, or all of the ocean gyres, the main ones that exist around our planet. You'll notice a couple of key things here. Things in the northern hemisphere move in circles, and they always move in a clockwise fashion. Well, why do you think that is? In the southern hemisphere, they move in a counterclockwise fashion. Well, why do you think that is? Here are some of the major pillars. An ocean gyre, what we're talking about, is the movement of water particles driven by circulation, and it's because of the wind blowing across the top of the water. So this is usually in an area of about 150 meters. So from the surface of the ocean to about the top 150 meters. And the way I like to think about it is, if you're cooling off a bowl of soup and you blow across the top of the soup, you'll see some movement of the soup from near your mouth, from the high pressure point to the low pressure point, but you're not stirring up the bottom of the soup, usually only the top part. Because the winds are only blowing this top part, so they're responsible for the movement of water, but only in that top portion of the ocean. what we notice is, this is kind of a key term, but a lot of nutrients and things get kicked up via this process, and it usually happens where the ocean water is pinned up, the movement of ocean water is pinned up against the side of a continent. So we have it here, you'll notice right here next to North America, next to Africa, near Australia. So whenever we have the collision of this water particles and nowhere for it to go, that motion kicks up a bunch of nutrients and particles from the bottom of the ocean there on these continental shelves. And that's key for marine ecosystems. A little bit more on that later, but I wanted to mention it here because it mentions it in the text. Does this seem okay for people? Okay, so I just want to point out a couple key things here. What you'll notice about this, it matches the same pattern because winds are the driving force. So here's the equator. So we have a lot of heat energy, and we're going up into the atmosphere and then down on this side, and then this is a high pressure area. From high to low, the winds are pushing in this direction and then clockwise. And you'll notice when we get to about different degrees latitude, it matches what you would actually see with the convection cycle for the air. So it's the wind is what drives ocean gyres, and so they're always going to go from high pressure to low pressure, just like the wind, and they're always going to go according to the Coriolis effect. Everybody feels okay about this? Great. Now we're going to look at what the convection cycle looks like inside of the ocean. And so these text boxes are going to go away in a second when this video shows. This is a short video, only 30 seconds. Oh, it totally went away. But the red is going to be hot water being poured in, and blue is cold water being pulled in. It takes a few seconds for the system to get set, but I want you to pay attention to what happens. So as student action, here's what I want you to do, is list some observations that you have based on what you see for this reaction. Everybody ready? I'll probably play it twice because it's a short video. Here comes the hot and cold together. Let me play it again just so you can continue to make observations. I heard a few people frantically typing, which I like. Sometimes people need to watch it once to process it, but make some observations about what's happening here. Pause it right there. All right, give me some of the observations that you saw. Yeah.
To start, warm water went to the top and the cold water went to the bottom.
The warm water started to rise. Does that make sense or no?
Yes.
Based on what you understand. And then the cold went down? Yes.
Once the cold reached the hot water would bring it up, so it started a current because the cold water, it would draw heat from the hot water, which would cause it to fall from the bottom to the other side, which would cause the cold water to rise. So
This is really good. Did everybody hear that? Give it one more time. That was excellent. Give it one more time. And then I'll repeat it too. But I really like the way you used it.
At the beginning, after the cold water fell and the hot water rose, the cold water began to draw heat from the hot water on one side, causing the hot energy, or the hot water to fall on that side, and on the other side, the cold water would start to draw heat from there, causing the cold water to rise, creating a current.
So we had this current being created because of the temperature. We have density and gravity. It's the same thing you saw when we did the flasks outside. Density and gravity moving down. As it moves down, it pushes other things out of the way. And so we're creating pressure, and a current is being created. In a likewise fashion, the hot water, as it moves up, we're creating pressure, and it's going. So tell me this. Does this look like what you would have expected based on your understanding of the convection cycle in air? I see some heads nodding yes, I agree with that. What is the same about air and water as states of matter? Yeah.
The warmer stuff is less dense.
Warmer stuff has less density. That's true. What about filling a container or flowing and that kind of thing? Yeah. They're both fluid in terms of they're able to move, and what we have is displacement, and we have motion, and so we're having a current being created. So what we're about to talk about now is this thing called thermohaline circulation. And what I want you to understand by seeing this is a look at the convection cycle. And what's cool is it's the same in water as it is in air. So hopefully this enhances your understanding of what we've already seen in air, but it's also nothing new. So when we talk about the convection cycle in the ocean, it's the same thing as what we're talking about before. All right. I want to show a video because I think this does a good job of explaining this. I got to move this out of the way so I can actually advance the slide. I want to show a video, and we've actually seen these people before. I felt like they described it really well with pictures in a way that would be better than me just talking. But here's the main things I want you to pay attention to. So we're going to look at this thing called the thermohaline circulation. You may have also heard it under the name the Gulf Stream. But I want you to get out, well, how does it come up with this name? I want you to look at the role of density, how density is in the ocean. There are a couple component parts. How does it regulate climate in Europe, which will come up. What causes the movement of ocean water from the Gulf towards Europe? That one you should hopefully almost be able to answer without watching the video. I want you to just give a quick characterization of the movement of water that falls according to density, which is that cold particles plunging. What is the influence does the thermocirculation have? I actually, by influence, I mean on ecosystems and on human processes, etc. And then the last one is, well, what's going on with climate change? This is a short video, and I want everybody to get 7 things out of this. Feel good?
The ocean conveyor belt and the Gulf Stream. Ocean currents.
Let me turn it up. It's a little too soft for the video. Too loud for the music, too soft for the video. Hopefully that gave you a second to write the questions down. Let me reset my slide.
The ocean conveyor belt and the Gulf Stream. Ocean currents have a direct influence on our lives. They determine our weather, our climate, and much more. The ocean currents and wind systems transport heat from the equator to the poles and operate like a large engine for the global climate. In the oceans, there are numerous currents. The so-called ocean conveyor belt is very important for our climate. This term describes a combination of currents that result in 4 of the 5 global oceans exchanging water with each other. They form a worldwide circulation system. The conveyor belt is also called the thermohaline circulation, with thermo referring to the temperature and haline to the salt content of the water. Both determine the density of the water. While the masses of water may be moved in part by wind, primarily the different densities of the global oceans are responsible for their movement. Warm water has a lower density and rises, while cold water sinks. The water's density also increases with a higher salt content. At the equator, the heat from the sun is especially strong, resulting in a lot of evaporation and thus a rise in the water's salt content. That is where the Gulf Stream begins.
Okay, I just want to pause it here for the first thing, for the first break on this. Thermo refers to what? Temperature, and haline refers to what? So we have a couple things going on. What contributes to the relative density of the ocean? There are 2 main things. The quantity of salt and the amount of heat. So the heat and cool thing we already understand. We've seen that many times already in our convection cycle in air. But now we're seeing it in water. The thing that's new is the amount of salt. So if I add 8 grams per 100 liters of salt of water, I have a certain density. If I have 10 grams of salt per 100 liters, I have a higher density, right? This makes sense so far? So when you have more salt, you have more density. If you reduce the amount of water, what happens to the relative density of the water? It gets higher, right? Because the proportion of salt, even though you don't change the amount of salt, goes up if you take some of the water away. Does that make sense to everyone? Beautiful. Here's the next part about climate regulation.
The Gulf Stream is very important for the European climate. Its length of 10,000 kilometers makes it one of the largest and fastest ocean currents on Earth, and it's very warm. At roughly 2 meters a second, it brings up to 100 million cubic meters of water per second towards Europe. A constantly blowing wind, the southeast trade wind, drives warm surface water to the northwest into the Gulf of Mexico, where it heats up to 30 degrees Celsius. The turning of the Earth and the west winds then direct the Gulf Stream towards Europe and split it up. One part flows south, another east to the Canary Current, and a third part flows north, where it releases a lot of heat into the atmosphere as the North Atlantic Current.
Quick pause here. So how does it regulate the climate in Europe? We'll come to that second. Let's deal with the other one here. What causes the movement of water from this area, towards Europe? How can you explain this motion? What moves the water? Wind. And why does it go? So we must be moving from high to low pressure, but what's the deal with this turn like this? Which direction is that? Clockwise, northern hemisphere, Coriolis effect. So if we move a bunch of hot water over towards Europe, what have we just done to the climate and weather in this place? It's much warmer, and you'll notice in Canada at an equivalent degrees latitude, it's much cooler than it is in Europe. And the reason why? Thermohaline circulation.
The water becomes colder there. Its salt content and density rise on account of evaporation, and it drops down between Greenland, Norway, and Iceland. There we also find the largest waterfall on Earth, the so-called chimneys, roughly 15-kilometer wide pillars with water falling up to 4,000 meters. 17 million cubic meters of water per second, or roughly 15 times more water than is carried by all the rivers in the world. This creates a strong maelstrom which constantly pulls in new water, and is the reason that the Gulf Stream moves towards Europe. Countless species use the Gulf Stream as a means of transport on their trips from the Caribbean to northern areas. But it doesn't just bring us animals. An enormous quantity of warm air also comes with it. In order to produce the same heat which it brings to the shores of Europe, we would need 1 million nuclear power plants. That's why we also call the Gulf Stream a heat pump. Without it, the temperature would be significantly colder here, at least 5 to 10 degrees. Instead of lush fields, we would have long winters and sparse ice-covered landscapes in Europe. In the last few years, scientists and pundits in the media have repeatedly expressed the fear that the Gulf Stream could come to a standstill due to climate change. Because if the polar caps actually melt, the salt content in the water off Greenland would fall, as would its density. The North Atlantic Current would no longer be heavy enough, and so it wouldn't sink as usual. In the worst case, that would bring the Gulf Stream, our heat pump, to a stop.
Okay, so the movement, let's just look at number 5 really quickly here. Number 5, what's going on with the movement of water falling? How much water is falling?
A lot.
A massive amount. Way more than all the rivers on planet Earth, way more than all the waterfalls, down to 4,000 meters. So a meter is 3 and some change feet. So it's going extremely far down. This is responsible for the movement and exchange of water across all 7 oceans. So unlike in the ocean gyres, where we're only in the top 150, to exchange ocean water across our planet, we're very reliant on the thermohaline circulation. That's how we're moving water from the lower parts of the ocean. Okay, so just quick on number 6. What animals use it? The animals use it and how? Fish, whales, they use it for migration. If you've seen the thing around Finding Nemo, they talk about this a little bit. That's a thing. What about people? There's trash, which is a big one. Boats use it in navigation. And then the climate thing is really important. They use the pronoun we in the video because this is a German person that makes these videos. So they're referencing Europe in here. But you wouldn't have societies that look the way that they look in Europe if it wasn't for this climate regulation. So it's really important for all kinds of industries, all kinds of cities, etc. I just want to touch this one for 1 second. If you melted some of the ice, you're adding more water to the area there, which changes the density in which direction? It makes it lower because you increase the amount of water to the relative salt. This is my last slide for the day here. Same thing. We have 1 minute to go here. There's no new information on this slide, but this is from the textbook, and I just wanted to show, because the video doesn't give you a whole look at the entire picture of thermohaline circulation. We usually like to start talking about it with the Gulf Stream here, and we move this direction, and then the density and gravity takes it down. This is where those chimneys are, and that moves. It's responsible for the movement across this entire area, and so this is moving so fast here, it pushes water all the way across all of this area, and then as it rises, we have it kick back into shape, and the ocean gyres are what's blowing it around the continents and moving it from one place to another. So here's just a nice look at the thermohaline circulation. Again, this is from your textbook. Questions on this? Excellent day, gang. We'll see you tomorrow when we'll talk about El Nino.